Okay, these are Unit 6, Day 12 notes. Start on page 31 of your packet, and we're going to look at two strategies for anti-differentiation, and that's long division and completing the square. And these have very specific patterns, and so they're kind of really narrow in focus. You can only use them in very specific situations. So we're still looking at how can you incorporate what you know about derivatives to find antiderivatives. That's still what our focus is. That's our essential question. So let's take a look at these patterns. So what happens when our U substitution pattern doesn't appear in the integrand? So for instance, this pattern is a U substitution pattern. We see a function here and its derivative up here, or at least some form of its derivative. I could have a 3x or a 10x or just an x and work out the coefficient details. But that's definitely a U sub pattern. So if you notice, these two patterns here don't share that same pattern. We're missing the 2x here. We have a totally different polynomial up top here, and so they require different strategies. So this one requires a completing the square in the denominator, and this one obviously looks a lot different than this one. This one requires long division. So how do we know and how can we distinguish between the two? Well, completing the square will be when we have just like a constant up here, and we have a quadratic down here, because completing the square is something you do to a quadratic. So that's the pattern to know that we have to use completing the square. Long division, if you remember long division, it's like having the fraction 17 over 2, and then you set up the long division of how many times does 2 go into 17, and you set up all that subtraction stuff. And so long division is when the numerator is bigger than the denominator. And from a polynomial standpoint, that means we have a numerator that has a degree that is equal to or larger than the denominator. And then we know that that is the polynomial equivalent of an improper fraction. So, so that's when we know we need long division. In either one of these strategies, these are useful antiderivatives. I've written them in antiderivative form. I know you've gotten familiar with reversing your derivative flipbook, but I just rewrote these in antiderivative form so that they're a little more easily accessible to you. Okay, so let's first take a look at long division. So this is kind of what I was talking about, right? How many times does 2 go into 17? And then we start to say, well, let's see, 2 goes into 17 8 times without going over. And then in our head, we kind of do this, right? 2 times 8 is 16, so we put a 16 down here. We subtract it. We get a remainder of 1. And we keep doing that until we either run out of digits here, or this number is smaller than this. And then we know that if we have anything other than 0 here, we have a remainder. So we know our remainder is 1/2. Well, our remainder is 1, but we have this fraction 1/2. So we can rewrite 17 divided by 2 as 8.5. And we don't need the plus sign if this is just numeric. But with a polynomial, we'll need to separate terms with pluses and minuses. So things to expect for this particular strategy. These questions are rare. They're usually on the multiple choice. There's 1, maybe 2 per test. So in other words, when you take an AP test in May, you may have a long division problem, or you may have a completing the square problem. Occasionally, you might have one of each. Typically, there'll be a natural log in the answer. Typically, if you have an x squared in the denominator, we don't in this case, but we will have an example like that. You'll have an inverse sine or an inverse tangent in the antiderivative. Okay, and so these are all indications then, especially with multiple choice questions, that when you see kind of the patterns in the answers, you might not have to do the whole process of the antiderivative process. So let's take a look. Let's take a look at how you divide polynomials. You've done this in algebra 2, but it's been a while. So if we think of this fraction, how many times does 2 go into 17? From a polynomial standpoint, we're saying how many times does 3x minus 1 go into 3x squared plus 5x plus 3. So we're going to set up the division to look exactly like this. So how many times does 3x minus 1 go into this? And so now it's about matching our leading term. So our leading term is 3x squared. We're close, we need an x here, so we're going to multiply by x to get the right power. And so when we multiply, just like multiplying by 8 times 2 is 16, we're going to go x times this polynomial. So x times 3x is 3x squared, x times -1 is -1x, and then we can go ahead and subtract it, just like we subtracted here. I'm using brackets because we have to subtract each term from the like term above. So when we do this, this minus this is 0, right? We always try to get that first digit to go away. That's really important for long division. And then 5 minus -1x is positive 6x. And so in this case, we have to go to another term here because this is still bigger than this. So we can multiply this by 2 to get this. So we're going to do that. First, we're going to bring down the 3. There we go. Then we're going to multiply by the 2. And so 2 times 3x is 6x. 2 times -1 is -2. We're going to go ahead and subtract that. And when we do that, this minus this is 0 again. 3 minus -2 is 5. We have nothing more to bring down. This is now smaller, right? This is 5x to the 0 power, smaller than this. So we have a remainder of 5. So the way we write that is plus 5 over 3x minus 1, just like the plus 1/2 here. So this is an equivalent expression for this rational expression. So the thing is this is easier to integrate than this. So we can integrate these two terms really easily. And then this term is going to be a natural log because it's a 1 over x pattern. So we're going to integrate that. So here we go. So let's do the antiderivative here. Let's first work with x, right? Bump up the power, divide by the new power. So that's x squared over 2. Antiderivative of 2 is 2x. Let's factor out the 5 here. We're going to do that, and then we're going to work with this. It's a u sub, but it's one of those u subs you can do quickly. So let's try to do that and see how you do here. So we're going to bring out the 5, and we know that this is a natural log. So it's, if we called this u, it would be the natural log of u. And then we know the du dx would be 1/3, or would be 3. So we're going to divide by that du dx, divide by 3, right? That's the equivalent of solving for dx and doing the substitution. You'd end up with a 1/3, and this would end up with being a 1 over u du. So there is the antiderivative for that rational expression. And what I did is I just rewrote it here. Instead of 5 natural log 3x minus 1 divided by 3, I pulled that fraction out front. That's probably how you would see it more typically. Okay, so let's take a look at this one. You stop the video, try this one on your own. This is still improper. The powers match, but again, the pattern for an improper fraction is that the top be of equal or larger power, the degree, than the bottom. And so this is bigger by a factor of 3. So go ahead and stop the video and try this one on your own. Okay, if you're tuning back in, I'm assuming you've tried this on your own and you're just looking at this to check the answer. So we're going to go ahead and do the long division here. This x minus 2 goes into 3x plus 6 3 times. So we multiply that by 3 and that by 3 to get this and subtract it. And when we do, 3 minus 3x is 0. 6 minus a -6 is 12. And so we're done pulling things down. We actually didn't have to pull anything down. This has a smaller power than this, so this is our remainder. Our remainder is 12. So we're going to write the remainder up here, and that's what we're going to find the antiderivative of. Again, this is a natural log. So again, because this is a natural log, because we just have a linear term in the denominator. Remember, if we had a squared term here, then we would start introducing some inverse sign or inverse sign, excuse me, expression. No, I take that back, an inverse tangent expression, because that's the one without the radical. So doing the antiderivative here, this is 3x. We're going to pull the 12 out. It's going to be, when we pull the 12 out, it's going to be 12 natural log of x minus 2. And then the derivative of x minus 2 is 1. So we're dividing by 1. So I didn't bother to put that fraction there. And again, that's doing that whole chain rule thing kind of on the quick, so to speak. And then plus c for your antiderivative constant of integration. Okay, let's try, this is still long division, right? The top has equal or greater power than the bottom. This has an x squared, so let's try this one. It's a little more complicated. This is where we're going to start introducing the inverse trig into the answer. So we're going to go ahead and set up the long division. We first have to multiply by an x to get the appropriate power, so we get x cubed plus x. Notice what I had to do here. I had to write this in pure standard form. And this is not really standard form because we're missing x to the first power term. So I had to put it in. And we need that because we have x cubed minus x here. So I have to subtract this from above. And so x cubed minus x cubed is 0. I have 3x squared minus no x squared, so 0x squared. So it's just 3x squared is going to come down. And then I have 0 minus x, which is going to be minus x. Okay, we still have a bigger power, so we still need to continue our division. So we're going to multiply by 3. Oh yeah, that one's got to come down. We're going to multiply by 3. We're going to get 3x squared plus 3. So we're going to subtract that. And we're going to get 3x squared minus 3x squared, which is 0. We're going to get minus x minus 0, which is negative x. And minus 1 minus 3 is negative 4. So this has a smaller power than our divisor here. So this is our remainder. So we're going to write our remainder up here. It's going to look like that. I could have actually taken the minus and put it here and then had x plus 4 in the numerator. But we're going to split this into 2 fractions anyway. So I can't remember what I did, but I think I left the minuses with each term. So we are going to integrate that. And so here we go. Let's integrate that. So this is x squared over 2 plus 3x. That's pretty predictable. And then notice what I'm doing here. I'm taking this and making a fraction x over x squared plus 1. That's going to be a u sub, right? Because we have some sort of form of the derivative up here. This is the u. And then we also have minus, oh, here's my u sub, okay. And then we also have minus 4 over this. So this is where the trig function is going to, the inverse trig function is going to come into play. So we're going to have an a of 1. It's right here. That's the 1 squared. And we're going to have a u of x. So this is our x squared minus a squared, or u squared minus a squared in that pattern of inverse trig functions. So this is my u sub here, right? My u is x squared plus 1. My du is, my du dx is 2x. We know the x's are going to cancel. When we solve for this, we know we're going to get a 1/2 in the integrand. So those things to keep in mind. I'm not going to go through all the steps, but we know we're going to have a 1/2. We know we're going to have a 1 over u. So it's going to be minus, because the minus was there, half ln u, which is x squared plus 1. So if you can make that leap without doing the u sub, that's pretty impressive. I'm going to let the u go through the u subs. You've done enough u subs. You can go through those u subs on your own. Here's where I want to concentrate our efforts. So if you look at, we're going to pull out the 4. If you look at this pattern, it's with the 4 factored out, it's 1 over x squared plus 1. And that's the inverse tangent pattern. So the inverse tangent says I should have this pattern of 1 over a, inverse tangent u over a. Okay, so that's the pattern. So my u is x, my a is 1. And so simplifying this, this is your final answer with the plus c. So that's the antiderivative for that polynomial rational expression. Okay, so now we're going to give you a different look. So notice the polynomial on the top is gone. We've got this really complicated looking thing on the bottom with a radical, which is a bummer. I'm going to rearrange it to write it in standard form. But this has all the hallmarks of an inverse trig relationship. The question is, which one? Is it an inverse sine or is it an inverse tan? Very rarely do they ask you an inverse secant question, so don't worry too much about that. I just wanted to put that one there just for your reference. So we're going to have to complete the square on this. You should be able to identify whether it's an inverse sine or an inverse tan just by looking at the denominator. Okay, So which one? Pause the video and kind of think about that. Refer back to those antiderivatives I gave you at the beginning of the notes. Okay, if you're tuning in, I think you've made your determination that because there's a radical in the denominator, it's got to be some sort of inverse sign. It's got to be. Okay, because the inverse tangent one doesn't have a radical, and one's not going to mysteriously appear. Okay, so things to expect, same thing, 1 to 2 per test here, like this 1 per test basically on the multiple choice. It's going to be one of these 2 answers. And again, maybe you don't have to do the whole thing to see the answer on a multiple choice, and that's okay. All right, so if you remember completing the square sets up a perfect square trinomial. So it really works with these 2 terms and picks the right C term, the right constant term to fit that. So that's what we're going to do. So what we're going to do is we're going to focus on just the denominator. I'm taking this out and doing some algebra here. So I factored out my -5. I'm going to ignore all of the calculus for just a second here. And I'm going to work on completing the square on this, this x squared plus 10x, okay, in isolation here. And I'm going to bring everything else along for the ride. Okay, so I'm going to give myself a little room here. So notice I just slid the +1 over, gave myself some room in the brackets. Okay, so I have to complete the square on this. So if you remember the completing the square steps, we look at the b term, we cut it in half, and we square it. That's what this is saying. Okay, that's the perfect square term, the PST. So half of 10 is 5, squaring that is 25, so I must have a +25 here. That's going to make this a perfect square trinomial. I can rewrite that as x plus 5 quantity squared. Okay, so what did I do here? Well, in this term, all on the left here, I really added a -125. Okay, that's really what I did. I started with this and I put a 25 in the brackets, and when I distribute the -5, I really added a -125 to that expression. So I got to come out here and make an adjustment. Excuse me, I didn't add, I subtracted because of the negative. I have a negative, well, add a -125. I guess I said that right. So if I add a -125 here, I got to add a +125 over here so that it remains mathematically the same as this. And the idea is this number out here doesn't matter, so it can be anything. So I'm going to rewrite this as -5 times the quantity x plus 5 squared, and then +126. Okay, and I am working towards getting it towards this. Okay, so this is my u. I just have them positioned in the opposite order, and this is my a squared. This is my u squared. Okay, so what I'm going to do here is I am going to rewrite them so that it looks like the pattern. And now I'm going to stick that back into the integrand. So my a is this, square rooted, because this is a squared. If a squared is 126, then a is the square root of 126. And if u squared is this, and the minus has got to be here, so the u squared is literally just the 5 times the quantity x plus 5 squared. Okay, then u is the square root of 5 times the quantity x plus 5. I'm square rooting this because I just want the u. Okay, and so I know I have, I'm just repeating this stuff here. We did that on the previous page. My du dx, if I distribute this, distribute the root 5, distribute the root 5, my du dx is root 5. So what I have then is, here is my integrand. This looks a little screwy because I've got a square root inside of a square root, but that's okay. So here's my a squared and here's my u squared. Now I have to do a u sub on this. And so what I need to do is, this is going to stay the way it is, but I'm going to solve for my dx. And I'm going to substitute out these things. So it's going to look like a squared minus u squared times du over root 5. Okay, in fact, I did a double substitution. I didn't have to substitute out the square root of 126. I just did. And now I'm going to write it like this. So I'm going to factor out the 1 over root 5, sine inverse u over a. So remember, my u is this, and my a is this. So that is the antiderivative for that. These are pretty involved. This particular example is really involved. And then I'm going to put a plus c on the end. Okay. So these are pretty involved. The tricky part comes in finding this coefficient, doing that u sub here and finding out that we have a root 1 over root 5 that comes out of the integrand. That's the tricky part. I think it was easy to see the spot in inverse sine. It might have been okay to spot this stuff. Getting the right thing that factors out of the right constant that factors out of the integrand is kind of the tricky part there. Okay, so try this one on your own. And I'm going to ask you the same question. You know it's an inverse trig because you have a what we call a non-factorable quadratic in the bottom. And you know it's not a long division because you just have a 1 up here. You just have some sort of constant up here. No higher degree polynomial than the denominator. So the question is which one? Okay, so go ahead and pause the video before you start trying to do anything with completing the square. Look at those inverse trig expressions and determine which inverse trig expression you're going to be using. Okay, if you're tuning in, I'm assuming you've determined which one it is, and it's an inverse tan. If you haven't started completing the square process, go ahead and pause again and start completing the square. Remember, we want to write it like this. That's the goal, so we can just plop things in place. Okay, if you're tuning in, I'm assuming that you've done that. The first step is to recognize that completing the square is a lot easier when we don't have a coefficient in front of the x squared. And luckily enough, we can factor a 6 out of each one of these terms. So I just did that right away. Okay, now I'm going to focus on the denominator. So I'm going to slide that over so I can have some space for completing the square on this. And half of 6 is 3. 3 squared is 9. I didn't even use brackets here because everything's positive. I added 9, so I have to subtract 9 to keep it equivalent to what I have in my denominator. So now I'm going to write this quadratic here as a perfect square. So I'm going to write it as x plus 3 quantity squared, and this looks like it's 4, which is nice because it is a perfect square. That's kind of nice. So knowing that this is the pattern, then I'm going to write it as a squared plus u squared. Actually, I have it written as u squared plus a squared. So, you know, a couple of things. We could swap these two, but there's a plus in between there anyway. So I'm just going to keep it as u squared plus a squared. Just kind of keep that in mind. Okay, I got the 1/6 out front. I'm going to start fitting this pattern now. So that's my u, that's my a. And my u, notice my u is x plus 3. So don't get distracted with that answer quite yet. And so just to talk about the doing a u sub, we don't have to because the derivative of this is 1. Okay, so we're not going to introduce any other constant into this expression because of that. But if you wanted to do a u sub, you could. Okay, back to this. So this is my u and this is my a. This is my pattern for an inverse tan. It's 1 over a inverse tan u over a. So 1 over a, 1 over 2, inverse tan, u over a plus c. And then I'm going to simplify this and call that 1/12. So there's the antiderivative for that rational expression. Okay, when we get into the classroom, then we'll talk more about these patterns. A lot, like I said a couple of times, a lot of times you can kind of not have to go through the whole process to see the answer, which is kind of nice. And that's really what the topic questions will help you kind of get a feel for.